Welcome to the fourth annual Scale container track for Scale for all things containers. We're now the containers and orchestration track. We used to be the containers and virtualization track, but people stopped submitting virtualization talks. I'm told people still do virtualization. How many people here still work on overt VMware? Yeah, that hasn't gone away. So, just if you want to submit a virtualization-based talk next year, we might take it. Just letting you know. I'm one of the three track chairs, the other two being Elizabeth Joseph and Stephen Wong. Stephen could not be with us for the obvious reasons. You'll see Elizabeth later on today. We've worked really hard to bring you a balanced set of content covering all bases, only to have our efforts entirely smashed by a little microscopic studded ball. So one of the things I want to say today is a lot of the speakers that you'll see today and Saturday and Sunday were swapped in at the last minute. Were people that I knew who had talks, and I said, this person canceled because work has suspended all business travel. Could you possibly do a talk about this? So I am going to ask you to be extra generous with your applause and forgiving of any preparation issues that anybody has, because a lot of the speakers you're seeing today may have found out that they were doing a talk at Scale 48 hours ago. But we will do our best for you, and we do have a full track today going all the way until 5 p.m., covering a lot of different things around containers and orchestration. So for our first talk, to give you a broad overview of understanding where we're all going with this, we're going to have Karen Bruner, who's going to talk to us about Kubernetes as a concrete abstraction layer. Karen is an expert in Disney, Warner Brothers, and Aesop's fables, and irresponsibility.
Can everybody hear me?
Yep. No. Try it again.
Try again.
It might be the mic is just too far from your mouth.
Oh, I do hear noise. Is that better? Is that good?
One check.
I'm talking. Can you hear? All right. Let me adjust it. Let's see. Will that hold? Closer? Is that good? Is that good?
Okay.
Does everybody hear me? In the back?
Yep.
In the front? In the middle? Okay.
Yay.
Thank
Okay.
you.
Well, welcome, Karen.
Thank you. And if unfortunately I do not have the excuse of being one of those people who only had 48 hours knowledge. I had a month or so, but I did finish my slides about 48 hours ago, so there you go. So I have a long history in I started out as a Unix sysadmin, going to the DevOps, system engineer, whatever, SRE track. I am finally no longer on call. I am sorry? A little louder? Okay. Is that better? No. Okay. Is that good? Is that better? Not better? I can speak louder. Oh, there we go. I just have to hold my hand like this the whole time. Is that good? Okay. Sorry about that. Okay. So after decades literally on call, I recently became the technical evangelist at the company I'd been working at. StackRox, we do Kubernetes Security. There is my plug, because they're paying for my trip. I am a totally sane cat lady. And on Twitter, and I'll post the links to the slides afterwards on Twitter and on LinkedIn, my Twitter handle is FuzzyKB. So obviously I have to talk about what is Kubernetes. Who here has actually at least touched Kubernetes, maybe? Pretty much, okay. Who here actually works with Kubernetes in production? Okay. Who here is running Kubernetes on different platforms, like either multi-cloud or on-prem? And okay. So obviously they'll tell you it's a container orchestration platform, which, you know, if you sit there and try to explain that to your grandma, is probably not going to fly. So this is what I think Kubernetes actually is, or at least what it feels like. It's kind of like a self-driving car for containers and workloads, but you know, it's not completely self-driving, and you get in different cars, stuff doesn't work the same, and if it catches fire, it burns for hours. So in this talk specifically, we will cover, and there are a lot of pictures of my cats. In this case, this cat likes blanket forts. We'll talk about the Kubernetes release cycle and the Conformance program, and then we'll talk about where the differences lie, which include storage, service load balancers, node lists, security options, a couple other differences, and more importantly, what you can kind of do to plan for these differences so that your applications can just be very portable. You don't have to craft custom manifest for every single application you deploy. So the Kubernetes release cycle, they release every 3 months at any time, because the releases, at any time they'll have 3 supported versions. Oh, I can hold, yeah, that may work better. It's a little awkward. Okay. Is that better? Okay. Let me get untangled now. Okay. Okay. I don't know. Okay. So I have no idea what's going on. Okay. So Kubernetes, they release every 3 months. At any time, they have 3 supported versions. There has been a proposal to support 4 versions, so be a full year of support for a version instead of 9 months like it is now. We'll see. It probably won't happen for the next release, but it's in discussion. And they have this really cool, if you haven't seen it before, there's this really cool interactive site for their release notes. So you can actually tune in, you know, you can do a bunch of different searches. You can say, I want security-related releases, any security features that came out or bug fixes that came out in Kubernetes 1.15 or 1.16. So definitely relnotes.k8s.io is really useful to visit if you're trying to figure out what's supported in the version you happen to be running. This is the current support matrix, just for the big 3 providers compared to vanilla Kubernetes. As you can see, everybody's on the default of 1.14, which is not actually supported by Kubernetes Foundation at this point. And interestingly enough, GKE was the last of the 3 to make 1.14 the default, which happened, I think, 1 or 2 weeks ago. And it's also interesting that Azure, AKS, is quickest to bring out the preview versions. So, see, the Cloud Nation Computing Foundation is a governing body for Kubernetes. They have a conformance program, so you can make your flavor whether you're hosting managed Kubernetes or whether you're creating a tool that will install unmanaged Kubernetes. They have a set of standards so that you can run these tests and say, hey, yes, I conform to everything. But it only covers parts of Kubernetes. Kubernetes is meant to be, it's very opinionated in its core functionality, but it's meant to be also very extensible, very customizable based on your needs, your actual hardware or cloud environment, and a lot of other factors. So that's the main reason we see differences between different providers. So the things that are covered under the conformance test are the kubelet behavior. And the kubelet is that process that runs on every node, and it's responsible for talking to the API server and saying, oh, I'm supposed to schedule this pod, and it needs these things. And containers come up, they have the right volumes mounted, and that sort of thing. And then it garbage collects everything. That's all covered by the conformance. Most core API resources are covered. The core resources are the bits you play with, like the config map, pods, secrets, namespaces, the building blocks. It also covers the app API resources, and these are built on the replication controller, on the pod replication controller. So these are deployments, daemon sets, stateful sets, batch API resources, jobs, cron jobs. These are not service-oriented containers. These are containers pods that do something and then exit. They're expected to have a ephemeral limited lifespan. And this also covers the standards for pod-to-pod and service networking. Any pod should be able to directly address any other pod without dealing, and even if the virtual routing it goes through proxies or whatever, but the pod should just know I can talk to this other pod at this address and not have to worry about it. And then the service, how the virtual IPs for the services actually work. So the things this doesn't cover are storage class and persistent volumes, because those are very dependent on what's available to you in what platform. Services of type load balancer, again, this is an externality that's, you have to support what you're in, and core Kubernetes can't really address that. So it should be you should be allowed to, if you have the right drivers, if you have everything in place, use whatever load balancer is available. Any APIs that require, for the most part, plugins, most controllers, or any kind of device drivers, for obvious reasons, not covered. And also, this is coming up more and more, nodeless Kubernetes platforms. So as an example, like I said, lots of cats. We cover, pods are covered, load balancers, not. So some examples. I ran a bunch of tests. These are the evaluation environments I used. I used the defaults for everything, with a few exceptions. AKS, you have to choose between KubeNet or the Azure Container Network Interface. I chose KubeNet. And for COPS, I chose the Flannel CNI because kubelet, you kind of need a VXLAN to work really well in AWS. And I didn't want to use, I would usually go to Canal if I had a choice, but I didn't want to just plug in network policies for a reason. Again, all of these are defaults. For obviously the first three are the cloud-hosted platforms. The latter three are self-managed. And I put them all on AWS as kind of a comparison just to see how even different providers that are using the same cloud infrastructure, basic cloud infrastructure, can differ. So we'll start with persistent volumes. These are storage that you have multiple options for storage. You can just do a local, what ends up being either a local directory on the node, or it's scratch space. So it's not stateful. If your container dies, data goes away. The node goes away, data goes away. So you provision an external disk from whatever service you have that can give you disk space. And persistent volume, if a pod dies and a pod comes up to replace it, it will move and follow that pod if everything works properly. So you define what kind of back-end storage you can use by using storage class, the storage class resource. And there's usually a default that's set up by every provider or every installer. But even these have some differences. So EKS, you bring up, you ask for storage, and it gives you GP2, which is their basic solid-state drive-backed storage. But in Azure and in GKE, they give you, the default is hard drives. And obviously, there's going to be a performance difference there, which you may not expect. Both AKS and GKE have standard solid-state drive options, but you just have to know to choose them. And if you want to make your apps portable, you probably want to change the default class so it's consistent across providers. COPS and OpenShift deployed on AWS also use GP2 solid-state volumes. Kubespray by default doesn't. The installer supports everything. Kubespray is really portable. It's really nice it'll run on pretty much, it supports almost any platform, and including on-prem, direct to hardware, so it's very flexible that way. But it leaves, even on consistent platforms like known platforms like AWS, it still leaves the job of actually dealing with the controllers, setting up the cloud-aware controller to the user. That's why there's nothing by default. It can be made to, you just run the standard AWS cloud controller, and it will magically work, in theory. So, like I said, one way to make this more predictable and make your persistent storage more predictable, use standard default storage classes. If in every environment you have the option between solid state and hard drives, pick one, whichever works best for your organization. Pick one and make that the default storage class. But you can also then create other storage classes that are optional, like maybe you want the default to be solid state, but for slower workloads where they just don't need the throughput, use hard drives. But just make them available, make it a separate optional storage class. Avoid provider, like the special Snowflake offerings. These are vendor specific, much more vendor lock-in. Thinking of things like Amazon's Elastic File System, which a lot of providers just don't have. It's their NFS implementation, hosted NFS. Most providers don't have an NFS implementation, and then also you'd be using NFS. And okay, some people just like to do that. I don't know. I don't anymore. You also have the option of running something like Ceph. Ceph is it's consistent across platforms because you use. You set up a cluster with node attached or host attached storage, and it manages doling out the volumes. And Rook is an interface that can run over Ceph. It's a lot of overhead, both in hardware or virtual hardware and in operations. But if you want really a consistent interface wherever you run, it's going to create a storage abstraction layer so that Kubernetes doesn't. You're not breaking the Kubernetes extraction layer when you hit storage. So that's one option that's more portable, but again, it's a lot more work to set up and manage. So next we're going to talk about service load balancers. These are also defaults. Again, a lot of cloud providers have a lot of different classes of load balancer, but they all act differently and they all choose different defaults. So the biggest thing, probably one of the most important differences is whether or not the source IP is preserved when it gets to the client. So if you have an internet-facing service and you want to know what IP address your client is from, either for audit purposes, for firewall purposes, or just to track where your users are, you would like to have the source IP. You'd like to tie it to a specific request. Also care about the idle timeouts. This can matter for a number of reasons. If you're doing a lot of gRPC, you would rather have longer idle timeouts. So Azure deploys their standard load balancer. And again, I just have a service manifest. I don't have anything special about it. It's just type load balancer. It will give you an Azure standard load balancer, which will preserve the source IP. It will do source natting. Their default, it's not, I don't think it's their standard. Okay, the standard default, and I've already forgotten this number. This number is either the standard for the load balancer in general, but I think AKS load balancers have a different default. No, I didn't write it down. But it's tunable. You can do anything from 4 to 30 minutes. EKS in Amazon, it gives you a classic elastic load balancer. This does not preserve the source IP. Default timeout 60 seconds. You can do anywhere from 1 to 4,000 seconds. GK uses their external TCP UDP network load balancer, and it does preserve the source IP, and I could not find any documentation about the idle timeout. It may be there. I dug, I couldn't find it. COPS and OpenShift, I'm not sure if OpenShift uses the standard AWS Cloud Controller, which is the piece that lies between Kubernetes and your actual infrastructure and manages provisioning, whatever you need. But I assume they do because they seem to default to the same behavior. They both, COPS and OpenShift, will by default give you a classic elastic load balancer. So differences in load balancers. One thing you can do in your service manifest is set external traffic policy to local. And this means that so service routing in Kubernetes by default kube-proxy sets up a round-robin routing if you have multiple backends for the same service. And it's, by default, it's just totally random. Even if the request comes into a node with a pod for that backend service, it's random if it'll hit that one or another one. This setting external traffic policy to local will force it to serve from a pod on that node. And if there is no pod on that node that responds, it just drops the connection. So you either want to do one of two things. You either want to make sure your load balancer is doing health checks, so it's only routing these requests to nodes that can serve this, that have the pod so that they can serve this request, or use a daemon set, which will put the pod on every single node. So your load balancer must support source NATing. Otherwise, it can't get the source IP. It's lost somewhere else. And if you have a load balancer that doesn't have source IP NATing, you can either check to see if your provider offers different load balancer types, or you can use, some of them support proxy protocol, which adds a string at the beginning of the request, but your application has to be aware of that. It has to be looking for that. It has to know it's going to get the proxy protocol header and be able to consume that. So usually you change the load balancer behavior by adding annotations to your service manifest. And these vary completely, for the most part, by cloud provider. So for an example, in AWS, you can use a network load balancer, which will preserve the source IP. It's just not standard. So you would add this annotation, AWS load balancer type, network load balancer, NLB. If you still want to use the classic ELB, but you want to use proxy protocol, and the classic ELB only supports proxy protocol v1, that's good to know. You can add an annotation for that to enable proxy protocol data on every single request. So I have a quick demo that may or may not be completely functional, but we'll see. And now I have to type with the microphone. Okay. I will try to, let me make the font bigger. I'm going to put this down for a minute. I have two terminal windows. I'm going to run this on Azure AKS, and this is the first column. Second column will be Amazon EKS, and then third column is GKE. So I just set up a really simple front-end demo. It's got an Nginx pod, simple service, and let me start tailing these logs. So you can see, obviously some of these have requests already. Okay. So this will work. So I'm getting the public IP for each of these front ends, and I'm just gonna, it's simple, plain HTTP, and this is what should happen. But you can see the last line. This is a private. Go ahead. You can't see. Let me make it a little bigger. Okay, this is, you can see these are private RFC 1918 requests, or IP addresses. So these are coming from generally within the VPC or within the cloud provider. Same here, same here. Playing. Okay, so now I'm going to set the external traffic policy to local on each of these. So this is a quick, it doesn't have to change, the change happens totally in the kube-proxy on the nodes, so it doesn't have to reprovision or change anything on the load balancer. So it's quick, it's quicker than I can type. Ooh, can't type. don't know if I curl, it will hopefully give me, oh yay, hey, that's an external IP address. However, if I do this in AWS, hey, I still get the same private IP address. It does not preserve the source IP. And then over to GKE, did I cut and paste it? Maybe I have a firewall issue. Okay, it may not come up. It will give me the public IP address if it works. So we can try. I didn't have any success. Unfortunately, I set most of this up last night, and I did not have any success getting the NLB annotation to work, because I didn't do that until this morning. We can see if it works better now. But I also set up a different service facing, or service with the back end. Oh, here's the IP address. Oh, 8 GK came through. Look, same public address. Actually, it's this one. Oh, hey, yeah, the NLB did finally come up, and it gives me the right IP address. So you can see here I have these two services. One is Nginx, which is standard, and then I created with the same backend labels, but a different service resource, which you can do. You can have multiple services that use the same backend with a network load balancer. And again, those are just using the annotations. So I just added the annotation for the AWS load balancer type. Okay, so that was my quick demo. Okay, so next we're going to talk about nodeless Kubernetes. This is pretty new. The open source, I wouldn't call it a standard yet. There are no standards around this yet. But one of the most popular, it's an implementation, but you have to still adapt it to whatever provider, whatever environment you're in. It's the Virtual Kubelet project. They are currently, so there are two issues here. For one thing, there is no conformance standard for nodeless Kubernetes. And also, nodeless Virtual Kubelet or any other implementation is probably not going to be conformant. The Virtual Kubelet team tested their implementation against the Kubernetes conformance test, and it's about 70%. The biggest standard portability issue is that there is no daemon set support. And the daemon set, again, it puts a pod on every node. But obviously, if you're just provisioning a virtual node to run one pod, you can't really do that. The problem, so that's this is a core functionality that's expected for Kubernetes, and obviously it just doesn't apply. It's not going to apply. Cloud providers are jumping on nodeless for a large degree. In AKS, it uses Azure Container Instances, and their implementation is based on Virtual Kubelet. EKS on Fargate, which was a big deal to some people when it was announced last December at reInvent, is not based on Virtual Kubelet, but probably not coincidentally, it shows a lot of the same behaviors. And GKE doesn't actually have a true nodeless. They have Cloud Run, which is actually under the hood the Knative function as a service. But even if you're using hosted Cloud Run, there's no direct interface. You could probably wrap it and make it act like nodeless, but they don't have support for that, at least right now. So common limitations for these managed providers, at least comparing AKS and EKS. As I said, no daemon set support, but that's going to be pretty standard. You cannot run privileged containers, and this is any kind of privilege, whether it's running the container as root, giving it host or network or process space access, anything, and especially not network admin capabilities. And the obvious reason is these are multi-tenant, and not just multi-tenant like a Kubernetes cluster, but AWS customer base multi-tenant nodes. You can't mess with that. And the problem with not having privileged containers, things like, even if you have a daemon set, say you're just doing it for pod monitoring or log collections, you can make that a sidecar in your pod and it will still work. But if you're using a network policy provider or a service mesh like Istio, those are expecting generally to modify the IP table rules on your node so that traffic does what it's supposed to do and are not available. They will silently not work. I don't know about Istio if you have a service mesh, how that, I assume that it just can't be seen. It's not going to certificate, it's not going to handle things properly. But network policies will just silently fail for that pod, even if it's part of a service, and even if it's talking to node, depending on the direction of the network policies. And unless you're looking for it and you mitigate for it, you may not know that's going to happen. You also have no node level monitoring visibility, which for security, you really want to be able to have, use something like eBPF tracing. You want to be able to see what service calls, what processes your containers are actually spawning, because if they are somehow, you have a bad image, they're compromised, whatever, that's the pod, the container is going to lie to you. You really won't need to see the operating system kernel to see what's going on, and that's not available. You kind of have a very fuzzy idea, but it's, for very strict security, it's not really a good option. So next we're going to talk about standard Kubernetes security features. What's on by default, what's available. RBAC is role-based access control is, if you're running Kubernetes and you're not using RBAC enabled and actually defining roles, please stop. It's pretty standard by this point. It's either optional or always on at this point in most providers. EKS is always on, and you can say, oh, hey, EKS is secure, but I think they just always turn it on because they don't want to have to manage. You have to enable it as a flag to the API server, and I think they just don't want to have flags that they either enable or disable, so it was easier just to turn it on always. And OpenShift it tends to be, they work very hard to be more secure by default, so it is also always on there. Otherwise, it's optional but enabled by default at this point on the other providers and on COPS and Kubespray. Network policy. This is how you're going to firewall your pod-to-pod traffic. Create rules about who can talk to what and who can't talk to what. It's optional in AKS, and there's a caveat. Both RBAC and network policy. When you have to turn these on when you create your Azure Kubernetes service cluster. You cannot turn it on later. So you really want to plan these clusters out, and if you're in AKS, because they introduce a lot of features that are also, you want to use them, you have to enable them at creation time, I would just, automate a way to migrate your workloads when you want to create a new cluster to use a new feature. EKS, it's user managed, by which I mean they have instructions for installing Calico. User applies the YAML himself and is responsible for all upgrades. GK, it's also optional, but you can enable it whenever you want. And they actually manage upgrades and everything else for you. You don't have to run any YAML, apply any YAML files. COPS, COPS and Kubespray, it just depends on what network type you choose. Both of them. By default, Kubespray uses Calico, so it's on by default. COPS does not. COPS uses KubeNet by default, so you would want to either choose a different provider altogether or install Calico manually. And OpenShift, they actually, this is a recent, I think it probably started with 4.1, I don't know for a fact, but they used to prefer their own network segregation until I think the 4.1 release. So now network policy, though, they've moved to make that the default, and it's optional. You can turn it off, but it is because you might want to have the legacy, their legacy policy. You might want to keep using it, but it is now enabled by default. And they do not support pod security policy. Pod security policy is, it's actually, there's been talk for a while, they're going to deprecate it, but they just haven't figured out what they're going to replace it with. So this is, pod security policy lets you set certain conditions. It will not admit pods that, say, want to run as root. You can set something like that in the pod or container security context. You can require that they use a specific UID. You can prevent them from doing any kind of privilege escalation. It's a little tedious to manage, and it's very limited in what it does let you control. So it's optional in most providers, and it's always on in EKS again because you have to run it. You have to enable it with an API server flag, and I don't think they want to make any of those user configurable. Other areas where you're probably going to see problem areas. So there are different types of Kubernetes admission controllers, and admission controllers are optional pieces of software that you can plug into the request handling pathway. So the API server, the Kubernetes cluster API server will get a request, and it says, oh, for this type of resource, I need to send it to this admission controller or this list of admission controllers. And there are a lot of different admission controllers, but the two that are probably most interesting to users are the validation webhook and mutating webhook. And the validation webhook is nice. It just says, I got a request of type pod, and I want to make sure, again, sort of this is what pod security policy does, although it doesn't, it has its own admission controller. It just says, oh, this you can have a rule that says, oh, hey, this container wants to run its root. No, reject it. So the API server just refuses to create that. And then mutating admission controllers are a little more interesting, although they're also more dangerous. You can say something really simple like, oh, every pod that gets deployed in this namespace should have a label saying it's deployed in that namespace. Or it should, you can, so it'll add the label for you. You can, if you program the admission controller, it will add the label for you. Say you want to, oh, hey, you're running Istio, and you want to inject the sidecar. That's exactly what the Istio sidecar injector does. It just, so that users don't have to change their deployment or pod manifest. It just gets every request for a pod and say, well, this namespace, Istio is enabled, puts another container in there that runs the proxy. Pretty much anything you can change or add or do to any kind of resource, mutating webhook can do. So security around those, even more important than validation. But there are also a lot of other smaller admission controllers. Those two, though, are going to be the ones that, especially if you're programming or you want some kind of standard, those are going to be the most interesting to you. Another difference are the enabled feature gates in Kubernetes. So a lot of features, especially when they're beta, you have to use a feature gate to turn them on. But even afterwards, even after they go to GA, it depends. I think they usually, I'm not sure if they always remove the feature gate or they just leave it for a while and leave it on by default. Anyways, so especially when a managed provider is releasing a new version of their managed platform based on a new version of Kubernetes, a lot of times they will disable even really desirable features by default just because they're not ready for them or they are not ready to test them completely. They're trying to preserve some kind of backwards compatible behavior maybe. So you kind of have to dig sometimes. You have to read a lot of release notes and make sure everything is doing what you need it to be doing. Some of them will even offer different enabled API groups. Again, as long as they offer that standard set and support it and it behaves correctly that we saw earlier, that's fine. But some of these are optional. So you can do kubectl API resources, and it will show you what API resources are enabled on your cluster. And it's less likely, but even different container runtimes can affect some very low-level changes. Mostly, the main differences, though, this is fairly standard. It's probably going to be in the allowed capabilities. These are Linux-level capabilities like netadmin or privileged or other. I'm blanking on the list, but netadmin is probably the biggest, most widely used in most cases. So these are less some of these are less likely to cause issues, but I think EKS, for example, was kind of late to the game in allowing mutating admission controllers, mutating webhook admission controllers. So they just turned it off, and it's very useful. Not having it makes, like I said, something like Istio, which is going to want to inject a sidecar. You can manually do that, but then you're manually adding it. So these are also, if you're using very new features, something you really need to look at for portability. So we saw for specific examples some way to maintain portability. Generally, making sure your clusters are consistent. There are some higher level things you can do. Some of these are nicer than others. You can just create self-managed clusters using a tool like Kubespray, or even to some degree OpenShift abstracts a lot of this. Kubespray, though, supports a lot more platforms, but it does leave a little more of the customization work to the user. And it really needs better installation instructions. Yeah, it's a lot of well, you run this command and then stuff happens, and now you have a cluster. And it's like, I don't think that's how do I, okay. So Sonobui is the tool that is used to get official, if you want to make your Kubernetes distribution officially conformant, you run Sonobui with a flag, so it'll run the plugin. Sonobui was originally created by Hept.io, so now it is part of VMware. It's nice, you can create your own plugins, though, that have certain tests. So what happens, you run it, you run the Sonobui command against a cluster, it creates a lot of pods and subpods, and it can take a long time to run. It's running a lot of tests, it can get very deep. I think it was just in Kubernetes 1.17 that earlier they promised that you could run the conformance test and not break anything, but now they don't make that promise, because they just want to run deeper tests. You're not going to run this against a production cluster, you're going to run it against a standardly configured cluster, but without production workloads. So it spits out a big file in XML, because who doesn't love XML, with all your test results. And it's very long, but I suggest try it out one time, see what's tested, see what's not tested. It does group the conformance test with their standard end-to-end test, so you just have to grep out the end-to-end. But you can also write your own plugins, stuff you care about, and it can be either core or not core. But what do I want these clusters to do? What standard functionality do I need them to have so I can make sure that my app can run on any of these platforms? Make sure, not just for good security, although definitely for good security, that you're enabling RBAC and network policy everywhere. This has two effects. It's good practice, but it also means you can just keep your manifest, all of the manifests for every piece of your component together, and they're standard, and you're not cookie cutting. You're not saying, oh, well, this cluster doesn't get a network policy, just apply them. And there is a weird thing about RBAC and network policy, and I'm like weird in that it's bad. So the resources are standard, so they will generally, if you do that kubectl API resources list, they'll show up. And you can create those resources, and the API server is super happy to create those resources for you. However, unless there's a controller that's running, that's actually paying attention to these resources, they may not apply. They will just, and if there's not, they will just silently, fail. That's not good. So test anytime you create a new network policy, anytime you create a new role binding or cluster role or whatever, test it. Test both positive and negative tests. Can I still run this? Can I not run this thing that I'm supposed to do? Can I not connect to this pod that I shouldn't be touching? And again, use consistent resource manifests across all your platforms. Make sure they're portable. You're still going to do a bunch of Go templates probably, but try to minimize that because it's easier to manage. And you want things to be, if you really want your environment to behave as much as possible in the same way wherever you run it, make sure it's defined the same way. And so you don't have especially don't have a bunch of different files. And I've seen horrible if then Go templates and you don't know what's going to happen. You want to keep them as readable as possible. It's going to make maintaining them and understanding what they're going to do much, much, much easier. Like I said, pod security policy is probably going to go away soon. Well, maybe not soon. Again, they don't really know yet what they're going to replace it with. One possibility is the Open Policy Agent Gatekeeper. It's an admission controller. At this point, it's just validating. I think there are roadmap plans to make it mutating too, but right now it will validate. Again, I want to create a pod that does this, and it will go through its criteria and say yes or no. it's getting a lot of traction. It's getting a lot of attention, but it has a very high learning curve to configure correctly because you're writing both OPA's Rego language, and you're also it creates a lot of custom resource definitions. In fact, you create a rule, and then you create a custom resource definition to apply that. It's complicated. So it may or may not be the standard. There's some simpler admission controllers. But one of the nice things about OPA is that you can limit it by any field, pretty much any attribute, to any resource type. So pod security policy, again, it has a very narrow set of fields which you can evaluate on. OPA Gatekeeper, it's pretty much, if it's in the manifest, you can say yes or no based on the value. So it's infinitely configurable, but with that it's complicated. You can also just write your own admission controller if you only care about a few things. But again, you're going to have to test it, you're going to have to maintain it, make sure it does the right thing and doesn't do the wrong thing. So I have a very long list of references. First off, I want to thank Brendan Cox, and I'm going to mispronounce his name, Madhuri Hachuri, for answering my questions about virtual kubelet on the virtual kubelet channel on the Kubernetes Slack workspace. There's not a lot of documentation. And in fact, I first asked them, and I think I reached out to them 2 weeks ago asking about it, and they're saying, oh, Brendan is literally checking the conformance test right now. We'll get back to you. And they were nice enough to get back to me with that. Virtual kubelet is 70% compliant with Kubernetes conformance. They're also, I assume the work will start also defining what the standard, I don't know if they're going to guide it or they'll leave it to the conformance say, but at some point they're going to have to define what should a nodeless platform do, what are these basic set of common functionality and features that these platforms should have. Because, like I said, right now you can't really predict. They do seem, both because of the nature of the nodeless environment and security reasons, they seem to often have a standard set of behaviors, but again, for now you're going to have to look out for it. It's nice to know that at least in the future, hopefully we'll know I can use this and I can expect this will always be the same, although this other thing may be slightly different. So there are 2 pages of references. I will put this slide deck up right after this. I will link it in my LinkedIn and on the Twitter handle, so you can peruse those at your leisure. And questions?
Yeah, but we only have the one hand open, so ask your question and people will repeat. So, what are you using that's like you're using ELOC, the nodeless evaluation?
Sorry, using what for nodeless?
You're using ELOC.
Yep, I was asking for, the question is for the nodeless, since I was talking to, I was working, sorry, easier probably if I run around and you just.
I just noticed you had Madhuri Hachuri up there, who's, I guess, co-founder of eLotl, and they're I don't know, is all your examples for nodeless problems, were they referencing eLotl, or is it just generic?
So I asked them about virtual kubelet. Virtual kubelet is, again, it's optional, but it's a basis for implementation. And then for whichever provider or platform you want to support, you do have to extend it. And it's a lot of the other cloud providers, smaller cloud. And so I'm going to insult somebody by saying this, but smaller cloud providers use virtual kubelet for their nodeless implementation. And I want to say, you can just go to the virtual kubelet link, which I do have my references off the top of my head. I think IBM does it. Alibaba, I want to say, does it. Azure is the big one that uses virtual kubelet for their nodeless implementation. AWS with their EKS on Fargate does not use virtual kubelet. I guess, I don't know what they do, but they rolled their own or something. Does that answer your question? Okay. Any other questions? And again, you can reach out to me later and I'll answer.
So if you're interested in going from like local host development to cloud, sort of what are some keywords that you can throw out for, this platform might make it easier to do that sort of migration?
So you're talking like Minikube, like you're just running it on your laptop or something like that? Yeah, I haven't actually. I've stopped testing that locally, so I don't have good answers. I know that a lot of, especially very low-level Kubernetes programmers are using Kind instead of Minikube because it gives you a lot more access to this. But again, I'm not sure how well it handles a lot of these kind of hardware platform dependent differences. Anybody else? Okay, thank you all for coming.